Hello again, everybody. Alan Shura here, March 26th, 2016. Motor generator self-looped. This is a motor with a reversed motor as a generator. They're identical. They're T45 motors from RC four-wheel drive. San Jose. And here, for those of you who may not be familiar with this, there are over 50 claimed self-looped systems trying to get energy production over unity, clean technology energy, through electrical means. And normally they would have a to do this type of research, you have to make a sort of a logical progression, and you have to go from the basic research. So this is what I'm doing. I'm doing some basic research here, and the basis of it is that there's DC generators, and alternating current generators and motors, and so there's only a few combinations. All of these self-loop systems that claim excess energy over and plus feeding back into itself, which would be infinite power, but it would also accelerate if that over unity was increasing. So we're looking at the theory of it, and so from my point of view, the logic of it has to be that there are no losses in the system. You're generating power and you're looping back. But if you use a rectifier to convert the AC back to the DC, there would be a loss. But here is a direct self-looping with two DC motors instead of AC DC, and there's no explanation as to why it should be an AC motor and a DC generator of a higher capacity, and then making the conversion back through rectification. So anyway, I'm going to start these motors, and we'll do a little input-output here. So here I have an AC adapter. It's 4.6 volts, maximum 1.5 amp. So I'll put that up to the power terminal connection, and this will start the motor. The hardest part is the connection. I don't know if it'll stay together. To self-loop, I can't reverse the polarity, or it'll cause a braking action and break the connection. So that's the problem I've always had getting up into the higher levels, and I'm still. But anyway, I've got the two things to connect it. They're the collars and plastic middle piece, but I hope it stays together. You can hear it starting to accelerate already. So with this one here, I'm going to take the measurements now. And we can see them side by side. The red one will be the amperage, and the blue one will be the voltage. So okay, it's 4.68 coming out of the wall. 4.68, but it's 4.24 volts under that load. of these two T45, that's 45 turn DC permanent magnet motors. And the input amperage now that's the kind of amperage I'm getting. So you can see it's a 20th of an amp. 0.51. 20th of an amp. Do the voltage again. 4.23 at a 20th of an amp. That's not very much wattage to run this setup, is it? Well, here's for the first time on this. I'm gonna try the self-looping. I didn't measure the output here, but I'll show some previous results. But for the first time with this one, I'm greater efficiencies that can come into this. Some magnets will increase the efficiency, and the logic that I'm basically showing here is that this is direct DC to DC. And also there's different results from the AC adapter to the battery. I've got some small batteries, some 6-volt batteries, and in the small 1-inch motors, which I'm not using now because they were simply too small, and a tight clamping would give different results, and the motors were inconsistent and starting to get a little bit worn. I got them for $1 each, but these new motors, which I'm going to start doing the testing on, I'll have more precise measuring equipment. I've got some stuff being ordered now. I have a power supply, and I got have some amperage meters. I haven't got them here. I did it to shorten this presentation, but I have constant amperage meters. This one you cannot do constant amperage, and you saw there was trouble trying to get the perfect connection. Well, I'll have the connection for constant metering of the amperage on further tests, and so there's more gain for the output, and I've seen that gain, and this is what I'm going to try to replicate. And we're trying to shape the magnetic forces in the center and use the forces that would ordinarily be lost to be used again in the energy transformation cycle. And if there's a little bit of induction, since on those small motors I achieved what appeared to be unity, and this is what I'm trying to verify with these larger motors now. I don't know where I'll go from here with this on the YouTube, but this is what I've got. It's 4.27. Now it starts at 4.68. So 4.27 on the input. You can't really tell the output unless you put a load on. So I've got some krypton light bulbs here. 3.6 volts. 3.6 volt and 0.75 amp maximum. Okay, we'll do it on the output side here. Well, hello again. March 27, 2016. Here I have a different setup where the input is lead acid battery, 6 volts at 4.5 amp hours. 4.5. It says cycle use up to 7.2 volts, 1.35 amp. these batteries never been charged, um, and one of them was run down when I did this test. And I'm using batteries, lead acid batteries, instead of the AC adapter. The AC adapter will limit the power. The last one was 6.75 watts maximum, 4.6 volts. So these are 6 volts. The difference is that the lead acid batteries, they can take a charge as well as providing power. So in this system, we're cycling power around in a self-looping way. So I didn't get the self-loop done with the AC adapter in the previous segment. But that was because I never had the negative connected here to the pole. But I'll start the system up now. Okay, the one battery is 5.5, 5.60. That was the weak side battery, I think. We'll check this one out. It's reading 5.90. Don't know if you can see that. .90. That's the starting voltage. Can't get amperage until the load gets on, but I'll start it up here. And this is starting just the one side. So here is one side from one battery, and here's the output side for the other battery. And what I'm testing here is another effect. It's an effect that's slightly outside called the bounce back effect, and it might be used in coils sometimes. But there's some theory out there now that there could be a bounce back effect in batteries as well. So that's why it's front and back end loading. And then rather than discussing it in terms of input and output, it then becomes a system power that migrates through the front end and the back end. So measurements are taken at both ends and from the battery of the current. And for the self-looping, you have the front end power here, which operates the motor, the front end battery, which I started there briefly, and you have the back end battery that powers this only in the opposite polarity. So that's the tricky part. It's in the opposite polarity. And then to loop it together, I attach the terminals here. The negative is attached here already. This is the negative wire for the self-looping, and then the other wire for the self-looping will be here. So you'll hear the acceleration at each phase. First, this one will start from this battery. Then I'll initiate the self-looping, and then I'll attach the second battery for the full acceleration. Okay, so now we've got the one motor started here. That's the second battery on the system, so it's sped up quite appreciably there. Now, basically all I want to show here is where I measured the amperage on this test. Okay, the amperage comes straight from the terminal here, and it goes straight back to the terminal there. And that's on the input side. Again, I put it on the positive terminal here on the battery. But this time I measure the negative because the polarity is opposite. But it's at the exact same point of contact, and you can see it's point 0.332, which I believe is considerably higher. We'll just check this other one again. We got 0.105. A quick check of the voltage. That's just to show how this was measured, because I have the results and I will show them, but I don't want to take a whole bunch of measurements and show it all, but I want to show how the measurements were taken, where they were taken. Okay, so the first battery is 4.91 volt, and the second battery 5.57 volt. So it clearly shows at this stage of migration that there's a much more powerful force coming out of the rear, the back side of this, the rear end of this, which is the generated power from the generator, is much higher than this. And that's the state of migration. But I found in my data that it balances out over time. Originally this was a weak mode battery. It was actually down to 5.14 volts. And right away there's a higher buzzing. And now it's self-looping, and the power is migrating. The batteries are communicating and balancing each other out. And the high output from the generator is being pushed back in eventually to the front end. And over time, the migration of the electrical power through the system balances out in the batteries. So I'll just put this down now and we'll get to the data. Okay, here's the generator, the two batteries, front and back end, motor and generator. The start voltage was 5.61 on the weak battery, 6.25 on the strong battery. After 5 minutes, the volts and amps were measured at the same points that you saw. After 30 minutes, the volts and amps were also measured, and the wattage was calculated. The average system watts over 30 minutes were an increase of 0.14 watt, an eighth of a watt increase. That's without the magnets, and with the second test I did magnets, so it's not exactly the same. and the magnets are put in the neutral plane. They seem to increase the amperage, but the velocity may have not have been the same. And it was duration of 5 minutes, 30 minutes, 1 hour. Data readings were taken the same way. The wattage showed an increase in the system on the input side over the migration, and a weakening on the output side. So there was, say, an increase over 30 minutes, the same as without the magnets. So make what you will of that. That was how the results were obtained using the system here.